All right, I think we are good to go. Good early evening, everybody. Thank you very much for joining us here. And I had asked about serving drinks, but they said no. So unfortunately, that it's not going to work. But thank you very much. If you've come to talk about simulations and learn more about AWS SimSpace Weaver, which was mentioned this morning and launched this morning in Adam's keynote, you are in the right place. I am joined by Roland and Mike, and two of our partners that will explain and go through actually two of the projects that they've been working on with Weaver. Over the next hour or so, we're going to go explore the problem space that Weaver was designed to solve. We will discuss some of the service's new and exciting features. And before I do that, I'm going to start with a bit of a confession, actually. So this is Confessions of an AWS Product Manager. I gave a talk last year at reInvent, a bit smaller than this, and we introduced two examples of scaling up simulations to over 1 million objects. And during that talk, I said this: instances that power this simulation and 160 Unreal servers that are running on those instances. We have our 10 instances here. Yes, so I was talking about 10 instance clusters and running massive simulations, and I never ever mentioned anything about SimSpace Weaver, and then everybody gave me feedback. They were like, well, can you just kind of, it's really cool, but tell us more about the distributed computing part, or what's going on with the distributed computing cluster, and just can you please tell us what the heck is really going on here? And at the time I couldn't, but this distributed computing cluster that we had set up last year was in fact SimSpace Weaver. And so here we are with AWS SimSpace Weaver, the first of our simulation-specific services. It is designed to help developers take their spatial simulations to new levels of scale and complexity and be able to create dynamic, seamless, and virtual worlds across multiple instances in the cloud with millions of dynamic objects. And you can also use your own simulators or popular 3D tools such as Unity and Unreal. On the surface, SimSpace Weaver addresses a simple premise for a rather complex problem. Developers simply want to build bigger simulations. I want to build a bigger simulation that resembles that of an entire city, right? But that is actually rather difficult if you want to simulate all the people, the cars, and everything else that goes on in that particular city. So, to understand why that problem is actually rather hard, let's make sure we're all level set on the basics. Number one, simulation is the evolution of a model over time, much like this car, and the position and velocity of which changes as it rolls down the inclined plane, which physics professors everywhere will rejoice that we are using their examples here at reInvent. Simulations come in many forms: fluid dynamics, weather, structural simulations. Adam talked a lot about these in his keynote this morning, and apparently there was some missing structural simulation on that bridge, which could have used some more of that, I guess. The spatial simulation is a bit different in that we are modeling objects with time and place, right? So like the spheres that are moving throughout this environment, each object has a position at a specific point in time, and these objects all share the same space, and they all interact with one another. As you saw there, the spheres actually sort of dodged each other, right? So if we're going to build really large spatial simulations that seek to reach real-world scale, where do you start? The first place you start is by creating your environment and essentially what the simulation would look like, and then also defining what the simulation does, how it behaves, the code that actually runs the behaviors of the entities. You then go to AWS and say, okay, well now I actually need to run this simulation application, and so I need to go grab an EC2 instance, deploy my simulation, and I'm going to push that as far as I can get. And maybe I can get 100,000 entities. And then I say, okay, well, let me scale up the compute. It's the cloud after all, right? So we go and grab another bigger instance. I'm sure there's a bigger one in the data center. And so we get to 200,000. And then we try again, and then you get to 400,000. And at some point, there just isn't a bigger instance. You have to think about, well, okay, at this point, I just need another instance. And so that now brings up questions like, well, now how are you actually going to do that? Well, if I need to go grab another instance, now I need to think about the hardware, I need to think about the networking, I need to think about synchronizing the state between all of them, I need to think about how to replicate data between the two instances, and I need to think about how to basically divide my entire simulation space, which all told is enough to make you want to flip your desk over and light it on fire. Or the other option, which you have now, is SimSpace Weaver. With SimSpace Weaver, we could take the simulation that used to be confined to a single instance and now distributed it across multiple instances for you in the cloud. We handle all the infrastructure, the networking, and setting up a secure AWS environment in which you can deploy your simulation applications. Scale up to across 10 instances that are woven together to create a single, seamless simulation environment. Now, where does it fit in the overall grand scheme of the simulation? So, understanding this is key to understanding where Weaver fits in. Weaver itself, or SimSpace Weaver, is the scalable simulation infrastructure. You are in complete control over what the simulation does and what it looks like. So the simulation logic, whether you want to write that in your own custom engine or you want to use something like Unreal or Unity, totally up to you. If you want to create a city with GIS or geospatial data that looks like Vegas, go for it. If you want to make one that looks like New Orleans, go for it. That as well is totally up to you. Or you can create a fully synthetic city. That works just as well. So the key to this is the SimSpace Weaver App SDK, which is how you integrate with the service, and one of the key service principles here. So let's dig into this a little bit. You can build the SimSpace Weaver apps by integrating the C++ SDK with your simulation code. The first type of apps are what we like to call the spatial apps. These are the apps that read and write entity data and entity state as the simulation progresses. Right? They are the core simulation logic. Then you also have a class of custom applications that can do other things that interface with your simulation. Usually, we use these to analyze the data from the simulation or read that data out of the simulation for purposes of visualization, which we will see examples of. You can launch these custom apps on every instance, or you can launch them manually. That's your choice. Now, what are we actually doing with Weaver? Let's take a closer look at the spatial apps. Simulations today look a lot like this picture. It's a single simulation application that manages all of the entity state of everything, essentially, in the sim at any one time. If you need more instances, you go get more compute until you can't. And then you're stuck. We are going to throw more compute at this problem, but we're going to do so in a slightly different way. We will take the simulation space and divide it up into what we call spatial partitions. Each of these partitions, which I have 4 of here that are all color-coded, will your SimSpace Weaver apps run in each of these spatial partitions. Instead of taking our compute power and throwing it at a single giant area, we're actually going to throw it at each of these smaller sections. And we're going to assign a set amount of compute and memory resources to each of these, and they will manage all of the entities within that particular area. This behaves like a simulation application today, except that SimSpace Weaver is what is maintaining the global state of all your entities under the hood for you. So, invariably, as things move throughout the simulation, because these simulations are intended to be dynamic, right? Cars will drive on the road and people will move from place to place. Entities need to cross these spatial partitions, or these boundaries, or they also need to cross instances. We help you with that as well. The entity state is stored in what we have as shared memory segments, which in each of the partitions are those blue rectangles, and then I have one particular rectangle representing my orange sphere that is going to transition from one partition to another. Under the hood, we transfer the shared memory segments and the data for those entities for you. So we're handling all that data handoff And this also happens across instances just as easily as it does across partitions. Again, from your standpoint and from the standpoint of the entities within the environment, it's one single seamless world. Now, we can move across the world, but we need to somehow be able to view it. So how do you do that? Well, SimSpace Weaver has a concept called subscriptions, which, using the custom applications that can read simulation data from the sim, we can create subscriptions on different areas of the simulation and read that data out to a client for visualization purposes. So that is how we create the nice videos and the nice visualizations and the interactivity that you'll see coming up in some of the videos later. Subscriptions also works for spatial apps. I often get asked, can entities interact across boundaries, or how does one entity know that there's another entity directly on the other side of the partition? Well, best practice is actually to have these spatial apps subscribing to a boundary area on either side of them so that you can actually actively simulate and acknowledge what's on the other side so you can preserve the interactivity. Okay, so those are the basics that we have on the service. So I'm going to stop talking for a bit, and I'm going to turn it over to Roland and Mike to explain how developers are actively taking advantage of SimSpace Weaver's tools to create virtual worlds at unprecedented scale. Doctor, here you go.
Thank you very much. I'm Roland Gerard, and I'm the founder of uCrowds, and that's a company that I founded 5 years ago. It's a spin-off of Utrecht University in the Netherlands. And it all started here with the Tour de France. This was a sports event being held in Utrecht. And Utrecht has a small city, and the municipality of Utrecht asked us, can you host 800,000 people in such a small city? And in order to answer that, we made some simulations to get some insights. So here are some pictures. And you see a simulation going on. And by doing the simulations, it turned out that at certain places, there was not enough capacity. So we had to broaden the road a bit. Or we had to install one-way bridges or one-way roads. So another example is of a Schiphol airport. They wanted to know, suppose that it will be 30% more crowded. Can we handle that in this environment? And also here, we could do simulations to answer these questions. Okay, so and in order to answer these simulation questions, we have been studying and creating a framework that can simulate big crowds. And this framework consists of a few elements. And one of these elements is that we have to have a representation of the environment in such a way that the computer can do quick simulations with it. And then it talks to a framework that consists of 5 levels of movement. And these are levels that comprise or describe how people are moving and behaving in a virtual environment. So at the highest level, we have AI, that decomposes a certain task into subtasks, such that we know for each task what the start and goal position is in an environment. Then in level 4, we try to compute an indicative route, which is a route that indicates how you globally want to walk from your start to your goal, while moving through a corridor in a building or on a street level. So once we have this route, what we do is iteratively, 10 times per second, we pick a point on this route which we follow. This gives us a velocity, so a direction and a speed, in which you want to move. But when there is a crowd, you cannot always move in that preferred direction, because you have to take into account everything that happens around you. So for instance, there is an imminent collision going on, so you have to avoid this collision from happening. Or maybe you are moving in a social group, like 2 parents and 2 kids. You want to stay coherent. You want to stay together while moving from A to B. So all these adjustments can be done at level 2. And then this yields a final velocity, which we can feed into an animation engine or a physics engine. And that drives eventually the visualization on your screen. So we created an implementation of this framework in an engine. And this engine is written in 100% Rust. And we also built some plugins for popular game engines, Unity and Unreal. And obviously, with AWS, we have been working on SimSpace Weaver integration. We also have another product with a very nice user interface called SimCrowds. OK, so this engine has been built for performance and interactivity. And these are some tricks we used. So we started off with a C++ engine, but it had some memory bugs, and we wanted to make it more safe and in such a way that it also scales on machines with many computing cores. So we moved from C++ to Rust, and we also moved from an object-oriented way of programming to a data-driven way. We looked at how memory behaved on machines, so we transformed our algorithms so that they became cache-aware. Then we carefully looked at memory management, so we made sure that we didn't do too many allocations and deallocations of memory, because it really destroys high-performance computations. Some computations are too expensive to compute during one time tick, and that typically takes 0.1 second. So these heavy tasks are decomposed into subtasks and then distributed over multiple frames. So the result is that we could simulate 400,000 agents on a consumer PC or 150,000 agents in the web, because Rust allows you to compile to WebAssembly. OK, but there was still a need for speed, because 400,000 is not enough. We wanted to do 1 million. So working together with AWS, unlocked an interactive digital twin that features a cloud-based simulation of a persistent world. So persistent means it stays alive. So I have been talking to many gaming companies, and they said, like, when you are creating a game, often you are walking around in an environment, and the game is created around you. And also the behaviors of other NPCs are created around you. So, but here, persistent means it should keep on running for the whole world. Interactive means that you can make changes to the world and change properties and take these properties and changes into account while the simulation is going on. Then there are real-time NPCs. We have a realistic photogrammetry environment that we can render in real time. It's visualized and animated on a client. And we worked together with Epic Games to also animate and visualize them on a client for 1 million visible NPCs. OK. But there were some challenges for. So, one of the ways to solve it is to eat the elephant in slices, because it's a big problem. So the first thing what we did was we split up the whole environment into cells, like Ritz explained. And then we increased the cell size so that there would be an overlap between different parts of the simulations. And since our simulations are deterministic, that is OK. And this overlap allows you to smoothly transition from one virtual machine to the other one. Then we created a navigation mesh structure and a simulation per cell. And by doing the careful synchronizations, we made sure that it all happened right. So the creation of these navigation mesh structures that is needed for the simulations, it can be quite difficult when you're working with GIS data, because it's view-ready in general, but not simulation-ready. So we looked at 3 examples. The first one is that we can make a simulation anywhere on Earth based on OpenStreetMap, so it's open data, with some satellite data. And what we did, we looked at the footprint of the buildings and used that as obstacles in our environment. While the second environment, we got some photogrammetry data from Maxar. And also here, we took the footprint of the buildings in order to create a representation of where people can walk. In the third example, we got data from Aerometrics. In this case, it's a representation of Las Vegas. And they gave us huge pictures in TIFF format. And we extracted some information from that. So each pixel denoted like the meaning of a certain area. It could be a street or a sidewalk or something else. And so we extracted the polygons that denoted the places where you could walk and then entered this into our simulation as input. So another challenge was, well, we could simulate 1 million in real time in the cloud. That was no problem. But then we needed to retrieve the data to a client. And if we wouldn't do anything about the data, so not compress it, etc., then we would need a 10 gigabit connection, which is way too much, obviously. So we compressed the data. We also came up with a customized protocol to send over UDP packets. And then we applied temporal and spatial sampling. So temporal sampling, an example is that agents or entities that are moving very far away, you don't need to send over all the data in each frame because it's just a pixel that moves on a screen. And if the movement is less than a pixel, then you won't see it at all. So these are some tricks to compress the data stream. So here is an example. You see the picture there with at most 10 megabyte per second. We could send over 1 million visible entities and also render them, which may still be a lot of data. But in most cases, you're not seeing 1 million people in real time because they are hidden by buildings and other shapes. So next we started working on the visualization and animation of 1 million NPCs with the help of Epic Games. So we used the Unreal 5 engine with blueprints, and we added a vertex-based animation and rendering on the GPU by the usage of their new Niagara's particle system, which was surprisingly fast. So we added some smooth interpolations and positions and animations. For instance, when you want to have a character standing still and it wants to go walking, there needs to be a smooth transition, otherwise it doesn't look right. We also integrated a few levels of details in the rendering to have high performance. So basically, agents that are very far away, you can render it with way fewer polygons. And agents that are just like 1 pixel on the screen, you can also render it with 2 triangles, if you do it carefully. So we eventually managed to create a simulation of 1 million people in real time, including the visualization. But the world is not enough. We want to do more. We want to make simulations at a world scale. So now we are trying to work towards a simulation of a whole country, which is technically possible. So we are looking for partnering up to collaborate. So we want to have an improved labeling of photogrammetry data so that the simulations are becoming more and more realistic. Also, we want not only to do real-time simulations, but also super real-time simulations. So for instance, we did a project in London St. Pancras Station. There are 32 3D cameras measuring the crowd flow. And we can, with a 3-second delay, put that information into our simulation system. And then typically we have 3 minutes time to make predictions of what will happen 15 minutes into the future, because that gives us enough time to make changes in the real world. And the changes are that trains are then arriving on a different track, or that you give passengers information about go 50 meters to your left and then take your train. So there is a need for super real-time simulations also in the cloud. Next, we want to have collaborations with companies working on other simulation components, like a traffic simulator. Okay, so I'll pass this one to the next speaker.
Thank you.
Good luck.
All right. Looks like we're going to be operational. Hi, everybody. I'm Mike Taylor. I'm one of the co-founders at Duality. And at Duality, we have built a digital twin integration platform to help our customers build robots, AI systems, even metaverse experiences. And I know if you follow the news and the shenanigans on some of those sites, Metaverse has got a bit of a negative connotation at the moment. If you'll give me a few minutes here, I'd like to try to rehab its reputation here. Looks like we might have a video compression issue. But I want to start talking about what our customers need in simulation. Now, our customers need large, complex, realistic simulations that reflect their operating domain. And the reason for that is they build robots and AI systems for the real world. As someone who used to do that in his career, I know how hard this is. It's painful to screw up in the real world. That's why you want to develop, train, test in simulation as much as possible. When it comes to the environments that they need, in a city environment, our users need a large variety of scenarios on which they can test and train their systems. That means from a city perspective, we need something very, very large and highly variable from top to bottom. From an environment quality perspective, we have a similar need. So our customers range from undersea robotics to aerial systems to everything in between, ground robots, even indoor systems with retail and manufacturers. The common thread for all of them is high quality environments. So when we think about a city, I need it to look good at the street level. I need it to look good at the top of the roofs. So drones can fly over a lot of different environments, and at their cruising altitude, a lot of things look good to their sensors. But when you start to land, you need it to be accurate. When we're talking about a city, though, also what we really care about are the dynamic obstacles. At least that's what the robots think of them as. We all think of them as cars and people. And that's the messy part of this world. That's what's really, really hard. And so if we look at the people here, actually, I do want a little bit of a shout out. All of the humans you see here are made with Epic's MetaHuman system. If you haven't looked at this, I highly recommend that you do. One of our customers is actually using our system, Falcon, along with MetaHumans to develop images that they've actually put in front of their consumers, and their consumers can't figure out if those are pictures of a real human or a synthetic person. Our customers love MetaHumans because of how accurate they look, but our customers also need them to behave accurately. And on a city level, what that means is their motion models can't be simplistic. They can't simply walk around the same block repeatedly. They need to be able to walk from one end of the city to another. And at the scales that we're all talking about here, that's quite the simulation challenge. And that's why we've been working with Weaver. Now, I said I want to rehabilitate the metaverse term, so if you'll give me a moment here. A metaverse is simply the virtualization of a physical 3D space, along with the assets and the interactions that are in there. Now, put that way, that doesn't seem too absurd. And if we look over our history, this is just the next digital transformation. Starting back when PCs started to become common and we had the beginnings of the web, that was us learning how to virtualize records. So I don't need a stack of papers on my desk. I now have Word and Excel to replace all of them. As our tech, our networking, and our compute got better, we started to virtualize communication and processes. That's why pretty much all of us here have smartphones in our pockets now. Probably the last time we talked with our bank, it was through a website. So now we're working on virtualizing spaces because we've hit that point with our tech and our compute and our networking. And done correctly, done in the right domain, you'd be forgiven for thinking that a metaverse is really just a very advanced simulation. And that's because that's exactly what it is. So we believe at Duality that simulation very much is the engine that powers the metaverse. And that simulation needs to run digital twins. A lot of folks know digital twins, definitely on the IoT side of things. So these are real-time or operational digital twins that tell you what is happening in the world. Where is my robot arm pointed? What is going on my factory floor? But there's a more powerful digital twin, a predictive digital twin that you can run in simulations. These twins let you ask more important questions, the what-if questions. What would happen if my robot arm was pointed here instead? Or what would happen if I replaced a computer or a machine on my factory floor? Now, the problem for our customers is metaverses do exist. If you have children the same age as mine, you actually know their names. Roblox, Minecraft, Fortnite, these are actually metaverses. They're fantastic for engagement. I play Fortnite with my son all the time. It's a great time. But from a business perspective, the value tops out at marketing and brand presence. On the other hand, there are simulators out there, and they're digital twin simulators. The problem for our customers is they lack scale. So they don't have the ability to pull in a wide variety of assets, of twins. They can't bring in multiple intelligent systems and the humans those systems have to interact with. And that's why we've built the metaverse to solve, we call it the real world problems, the problems of our customers. It's a metaverse is composed of digital twins instead of just avatars. It provides accurate and deterministic simulation so that you can generate realistic data, data that's indistinguishable from the real world. And the twin simulator that powers this for us is Falcon. So this is our baby. We all think it's pretty wonderful. Falcon loads your worlds, the assets inside of them at runtime. Just like Microsoft Word didn't show up on my computer with my thesis already on it, but it can run it, Falcon can load whatever environment you want to hand to it. The robot, the quadcopter that you see here, the computer vision system, all of that is instantiated at runtime based on a USD scenario system, which means that a roboticist like myself can edit human-readable files to change this virtual world. And most importantly, get the data out of it that I need to make my system better. And so what this allows us to do is help our customers end-to-end, starting with acquiring the digital twins that they need, managing them, allowing them to simulate those twins and get that crucial data out, data to train their systems, data to understand how their systems are behaving. And that's the view that we wanted to bring into this project with SimSpace. Sorry, it looks like the audio's a bit loud here. We didn't want to simply integrate Falcon and SimSpace and talk to everybody about the stats. We wanted to talk about how tools like this can answer actually very, very important questions. Questions like, how can smart cities that are starting to come online and intelligent vehicles be combined to tackle problems like reducing the time it takes for an ambulance to navigate a city like this to get to someone in distress? And our first step along that path was pulling in a digital twin. And so what we brought in was City Sample from Epic Games. Now, this is an example city that Epic put together to highlight what's possible with Unreal 5. And spoiler alert, a lot's possible. This city was built with Houdini, procedurally generated. The end result is a world that measures roughly 4 by 5 kilometers in dimension. It provides 260 kilometers of streets, 7,000 unique buildings. Buildings, as you drive past them, you can actually see in the windows of the rooms. Not just as a picture, but with active parallax. It's really quite impressive. 100,000 vehicles, realistic top to bottom. Out of the box, City Sample comes with 50,000 of Epic's metahumans wandering through the world. What we wanted to do on this project, among other things, was use Weaver to really up that count, and to do so in a way that didn't crush our local machines, so we could leverage the cloud to do it. So on this particular project, we actually played the role of Duality, but also as one of our customers. So we worked on the integration with SimSpace Weaver, but we also built all of the autonomy systems that our customers typically build. So the routing system to figure out how an ambulance can get from where it is today to a person in need. The autonomy system to run that ambulance along that path. The dispatch system to figure out which ambulance should be deployed. And we did all of this heavily leveraging Weaver in its local mode so that our teams could work on both the integration but also the simulation itself without necessarily needing to connect to the cloud. The architecture that we put together supports up to 10 workers across this world, evenly distributed across the entire space. Each worker supports up to 16 partitions, again, equally distributed across that geographic area. Now, what Weaver allows us to do is look at all these separate simulations, each partition running its own instance of our Falcon simulator, but our clients can talk to it as if it's one seamless integrated simulation. And so what we did is, as Ritz mentioned, we wrote a custom communication app. The job of this app is to talk with all of the Weaver workers and partitions and communicate to another instance of Falcon, a client, that is running our EMS scenario. So every time step, every tick, it reports out the location of all of the entities that SimSpace is managing to this client. So now the client, that in this case, on the EMT scenario, is running a smart ambulance. The client can render all of the people, all of the cars, everything that SimSpace is managing for us can render both for the viewport but also for the sensors on board. However, that client doesn't have to take on any of the simulation load of simulating those complex humans that in this case can walk from one end of the city to another. The result is this. Now we have a simulation to ask the questions that we want to ask. As we look at this world, as we trigger an emergency in this world, as we try to figure out which ambulance can get there. We can start to ask, well, I've predicted 3 minutes and 12 seconds to make this route. How long will it really take? What's going to happen if one of these humans makes a different choice? Or more interestingly, what happens if a human that's playing this game along with me, not a simulated human, but a real live human, does something different? So in this case, you can have a human come in and behave as a traffic officer. There's not a lot of models, real good models of the human brain. If you understand what a traffic officer might do, why don't you ask them to join the simulation and do the job that they're trained to do? So what we find out is, as our intelligent ambulance drives down this route, of course, we can see all of the SimSpace managed people, we can render them in our sensors, and we can find out that for this particular run, instead of the 3 minutes and 12 seconds that we predicted it would take, in this particular occasion, it took 3 minutes and 5 seconds. And this is the kind of data we need to come out of this. My latest version of my routing system is overestimating the time it takes me to get to my system or to get to this person in need. I can move on and try to go improve it. And I just want to wrap up with a comment about data. All of this is in the service of generating the data for our customers that they need to, again, develop, train, and test their systems. They need data that is indistinguishable from the real world, that is information-rich and intentional, with the goal being better ML systems, better robotic systems, more robust systems that hit our streets. With that,
Thank you so much, Mike and Roland. Look, it's really been a pleasure working with both you and in your teams. I think we've just about managed to break like every existing simulation tool out there as we try to hit these impressive levels of scale. So this is, but it's only the beginning. So this has been a lot of fun, and I look forward to continuing to work with you and your teams. I want to talk about time for a second. Because being able to keep track of time is actually a bit of a human obsession, right? After all, we need to know when and where to be so that we can be at every reInvent session that we want to be at. And Mike, you gave us a bit of a history lesson. I get to do one too, because keeping accurate time is not always easy. And one particular story I like goes all the way back to the 1600s and 1700s, and it revolves around the ability to determine your longitude on the Earth. And in order to do this, ships mainly relied on dead reckoning. And if you actually try to do this calculation, you need to kind of know, A, how fast the ship is moving, B, which direction it's headed, and C, how much time has gone past from the last time you tried to do this calculation. In theory, you could think about this as a basic kinematics problem. But keeping accurate time is actually really hard to do at sea. And so what you end up happening is ships that just kind of bounce all over the place, not really knowing exactly where they end up, and then sinking because they crash on the rocks, right? It's called dead reckoning for a reason in here, because the actual clocks, or how you would try to keep track of time with like a pendulum clock or like an hourglass, don't actually live up to the extreme conditions of being out at sea, the movement of the ships, the temperature of the water, temperature differences and such. However, it wasn't until the 1730s when John Harrison had actually invented a highly accurate chronometer that ships were finally able to determine their precise position anywhere on Earth, and the explosion of trade happened and such. Now, why are we talking about keeping time? Because time is very easy to keep track of when everything is on one instance, right? If it's all running on one instance with one simulation application, there is always one clock and it's always moving at a predictable amount, at a predictable rate. As soon as you start to distribute this simulation across multiple instances, or even breaking up partitions, now you start to come to a problem where you have to keep everything working in time synchronization with everything else. Because if not, the simulation just stops making sense. For example, and we're going off script here. You want to catch the water bottle? Okay, there, go for it. There you go. Mike is able to catch the water bottle because we are interacting in real time. He knows exactly when I throw that water bottle, and he can respond accordingly. If, for example, we were on different servers, and Mike was 5 seconds behind me or 5 seconds ahead of me, he would have really no idea at what time I actually threw him the water bottle, and as a result, he could never really respond. Like, for example, if Mike was 5 seconds behind me and I threw the water bottle into the past, what happens when Mike actually realizes the water bottle shows up? Does it like come back to me? Does he never see it, right? This is just like a paradox that will make your brain explode. So at the end of the day, you don't need to worry about this when you distribute your spatial simulation across servers because we solved it for you. So SimSpace Weaver keeps your entire simulation time synchronized no matter how many servers you distribute it across. Whether you want to run the simulation at 10 hertz, as Roland was saying, 15 or 30, you can run the whole thing even in lockstep if you want, so you don't end up shipwrecked on the rocks. So from keeping track of time to saving time, let's talk about one of the features of SimSpace Weaver that was a big request of customers who were testing this thing early on. During testing, we had a lot of customers who were saying, look, the service is great, I can expand my spatial simulations, but it's taking me a lot of time from when I go and make a code change to when then I have to go deploy that on the cloud, then I can see the result of my change, and then if I don't like it, I have to go all the way back, and this entire process is taking me way too long. Okay, how does one then take a service that is inherently intended to run in the cloud because you have to run on multiple servers and run it, for example, on a local device, which is essentially what customers asked us to do. They said, I just want to run the simulation on my laptop, see that it works, and then when I'm done with it, I will upload it to the cloud. So we set out and we developed SimSpace Weaver Local. As Mike was alluding to, this is very useful for teams while they're in active development. With SimSpace Local, you can run multiple spatial apps and also agent applications to view your simulation right on a laptop. If you caught my AWS on air earlier today, I was running a simulation in local mode with 16 partitions on a very, very beefy Alienware laptop. But you can run 2 partitions, you can run 4, you can run as many as your laptop can handle. Here's how it works. Number 1, you integrate with the app SDK that we talked about using the same APIs that you will use when you move to the cloud. Develop, test, iterate locally as many times as you'd like, and then package and build your application for the cloud. When you're ready for scale, upload that to the cloud, and off you go. You're using the exact same APIs, so you don't even have to rewrite your applications. The best part about the whole thing is this is absolutely free. Use this feature. I can't stress that enough. Speaking of these tools, we've seen how we've been really leaning in on the 3D engines, right, to bring these virtual worlds to life. What customers don't want to do, however, is have to go through all the work of integrating SimSpace Weaver with the engines just to get started to then build simulations. After all, the entire premise of the service is to let you spend more time coding and building content and less time worrying about the infrastructure and the connections and how you're going to get to that point. That's why today I'm also very excited to announce our 3D Engine plugins with Unreal Engine and also with Unity. These plugins make it possible for anyone to get started building SimSpace Weaver simulations with either engine right away. And we have samples with each engine available in preview starting today. Okay, before we close this out, one question I'm sure you're thinking is, you have this amazing new service. It probably has a very complicated model of how you're going to price it. What's this thing going to cost me? The answer is, it's actually not that complicated. It's quite simple. You get charged for the instances you use when you use them. If you need to run a simulation with only 2 instances, you pay for 2 for however long you want to use them. If you need 5, pay for 5. And if you need to scale out across all 10, pay for 10. No upfront commitments, no fees, no licensing costs. The SDK is free, the integrations are free, and local mode is free. Where to find us here at reInvent tomorrow. If you want to actually get hands-on with some of the demos that we've been talking about, we've got both Roland and Mike's demos at the EC2 kiosk in the AWS Village. We'll also be at Launch HQ. Launch HQ tomorrow 1 to 2, AWS Village 2 to 6, and also 10 to 1, so you can get yourselves hands-on. And then, Mike, you're going to do a deeper dive on the actual demo and the integration and some of the unique challenges that you guys faced. That'll be Thursday at 2 p.m. And I think with that, we will be opening it up to questions.